Welcome back. So the next sequential circuit that we'll be designing is what's known as the sequence detectors. Again, these form a very important part, especially in the digital communication, and that are often used in connection with error detection and error correction at different layers of the TCP protocol. So take an example. We try to design a sequence detector. Not actually design. By design, I mean here we'll be actually writing a VHDL code to design a sequence detector that detects this sequence 101 continuously in a general data stream. So you have a general real-time data coming from some source, and every time you detect the sequence 101, it's a 3-bit sequence, your output should go high, fine, for one clock cycle. But you continuously are looking for this kind of a data stream. This kind of a sequence in the data stream. So this is a timing diagram here. I have drawn the clock. There are multiple clock cycles, and this right here is the input data, the data stream that is coming in real time. Let's call it BI. Fine. So right now my data stream is 01, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, and so on. It's continuous. Fine. And I'm looking for this particular stream 101. As soon as this sequence is detected in the stream, my output will go high. So let's try to plot the output B naught. Fine. Now the first bit in this sequence is 1. So in the first clock cycle, the sequence is 0. So obviously my output will be 0. And I have not detected the required bit of the sequence because first bit is 1. Fine. So output is 0. Second clock cycle, the input is 1. So I have detected the first bit of this sequence, but my output is still 0. Fine. Then in the third clock cycle, the input bit stream, it reads 0. This is the second bit of my sequence. So in this third clock cycle, I have detected the second bit of the sequence, but my output is still 0. Fine. Then in this fourth clock cycle, the input bit is 1. Fine. And this is the bit I was looking to complete my sequence. Now all the 3 bits of my sequence have been detected. So output will now go high. Fine. And here I am assuming that as soon as the output 1, I mean the bit 1 is detected, the last bit of the sequence, in the same clock cycle, my output will go high for 1 clock period. Something like this. Right? It may be interpreted in a different sense. Okay, once you have detected all the 3 bits of the sequence, then in the next clock cycle, your output should go high. Something like this. If I draw it alternately here, that would mean some kind of this behavior. It is 0, first bit detected, second bit detected, third bit detected, then after output goes high. But as of now, we'll be designing it in this sense. Fine. Means as soon as the third bit is detected in the same clock cycle, the output will go high for exactly 1 clock cycle. Fine. Now after this, you see we are continuously looking for these sequences 101. If a first sequence is detected, then immediately after this you will start looking for another sequence. Now the thing is that the last bit of the current sequence which has been detected, it also acts as the first bit of the next sequence that you are looking for. Fine, because we are continuously looking for sequences 101, 101, 101. So the last bit of the current sequence that you have detected will also be the first bit of the next sequence that you are looking for. What I mean by that is by the end of this clock cycle right here, the first bit of the next sequence, it has already been detected. Fine. So 1 has been detected, then I'm looking for 0. So 0 is here, but my output will be 0. Then third, again another bit is 1. So again my second sequence is complete and my output will go high exactly for 1 clock cycle. Again, I will start looking for the sequence 101. And again, since the last bit detected here is 1, it will also serve as the first bit of the next sequence. But here in the next clock cycle, I have a 1. So the sequence is broken here. Output will be 0. Now from here, again, I will be looking for the sequence 101. Just my first bit is detected. Next bit is 0, which is the second bit of my required sequence, but output will be 0. Third bit is again 1. So output will go high. Then again, this one, which is the last bit of my current detected sequence, will serve as the first bit of the next sequence that I'm searching for. But again, then in the next clock cycle, I'm having a 1. So again, it will be 0 and so on. So this is the way my output will be traced. So this will be my B naught. An important point here is, two important points rather. First, as soon as you detect the third bit of the sequence of the desired sequence, which is 101, in the same clock cycle, your output should go high. Fine. And second important point is, since it's a symmetric sequence that you are looking for 101, so the last bit detected of the current sequence will also serve as the first bit of the next sequence that you are looking for. Fine. And accordingly, you will have to, and accordingly, you will trace the output here for a given bit for a given data stream. Fine. Now we have to code it, we have to design it, and we have to write a VHDL code for this. Right? And obviously, the first step is we have to capture the state machine, the finite state machine, wherein we actually have two methods. We can either capture it as a Moore machine, or we can capture it as a Mealy machine. Or again, repeat, in the Moore machine, once you are in a particular state, the output is defined. But in a Mealy machine, the output is conditional. So in a particular state, what your input is, that will determine what your output is going to be. So this is the main difference between a Moore machine and a Mealy design of the machine. So let's capture the finite state machine. Let's first capture the Moore machine. Or what can we can see the Moore design. And I'll choose an arbitrary state to start with. Let's call this state anything. Let's say let's call it A. This is my initial state as specified by this small arrow. Fine. And this is the first state, and in this state I am yet to detect any sequence. So obviously in this state, being a Moore design, the output is going to be 0. Now I have to determine from this state where I can move. Remember, my sequence that I'm looking for is 101. So if my input bi is 0, I will continue stay in the same state. I will continue to stay in the same state. Fine. But if my input is 1, it means the first bit of my sequence has been detected. So I will move to another state. Let's call it B, wherein we typically show it like this slash, wherein the output is still 0. Fine. But I have detected the first bit of my sequence. So this particular state, state B, it basically means first bit detected. Fine. Now the next bit I'm looking for is 0. Fine. And if I do receive that kind of a bit, so it is something like this. If my input is 0, which means second bit is detected. So I will move to the state C. Still my output is 0, but state C specifies that second bit of the sequence is detected. Fine. But if in the state B, if I receive a 1, this means the second bit of the sequence is not detected because it would have been detected had it been 0. But I am receiving 1. This means the sequence has broken. But at the same time, since input is 1, it means that the first bit of the sequence is detected. So I will stay in the state B because B corresponds to first bit detected state. Right? Now from state C, I will move to state, let's call it D. And this state, when my input is 1, which means the sequence has been detected. So D means third bit detected, and hence the entire sequence has been detected, which means in this state my output is going to be 1. Right? But we have to make a complete machine, complete finite state machine. What happens if in state C I have the bit as 0? In state C I have detected my second bit, means first bit 1 detected, second bit 0 detected. Now I am looking for 1. If I get a 1, I will move to state D, wherein my output will be 1. But instead of 1, if I receive a 0, which means the sequence has been broken, and I have not even detected the first bit of the next sequence because first bit is 1. So if input is 0, the transition will be something like this. I will have to restart the entire thing from the state A. Fine. Now in the state D, again there can be two conditions. Please remember D means the third bit of the detector sequence. It also means the first bit, if it is one. Maybe I should not generalize it here because it may be a possibility, it may not be a possibility. What I mean to say is when I reach to state D, fine, it also means that the first bit of the next sequence, maybe I should write it, huh? So this also means that the first bit of next sequence detected. Fine. So if in this state, if I have input as 0, I will move to this state C, which means my second bit of the next sequence is also detected. But if BI is 1, I will move to state B, which means first bit is detected. So this is basically in direct connection with this kind of timing diagram, the one that I have drawn here. And based on this, I have come up with a state machine which captures the behavior of my sequence detector. Fine. Now that you have the finite state machine, you can easily code it it's the same design strategy wherein you first have the similar, you start with the library declaration and entity. Here it will have clock. Like I said, clock is implied. You will have the input as bi and you will have the output as b naught or whatever variables you want to use. So I will directly start from the architecture. So architecture, FSM of, let's call it string detector. The entity name is fine. In the entity, I have defined 3 ports: clock as usual, BI as input data stream, and B naught as the output. And that B naught will go high only when the sequence 101 is detected as per the description of the problem. Fine. So the first thing that we do in the architecture is we defined the type. So type, let's call it state is. So I have 4 states here: A, B, C, D. Then as usual, I will define 2 signals by the name previous state and next state. And these will be defined of the type state, which is a user defined data type. Fine. Then I will begin. Begin my first, I will have a process for the clock. So it will be simply if clock event and clock is equivalent to 1, then previous state is equivalent to next state. So this process is for the implied clock, huh? And if and process. Fine. Then in the next process, I will actually use a case statement like we have been doing. Huh? So this will be my main process wherein the sensitivity list will have the previous state and it will have the input bi. Then I will begin, then I will define the case. So case with previous state as my identifier is. Then I will define the multiple values that this identifier can take, starting from the first one when it has a value of a. Fine. So when it has a value of a, the output, let's say if you have called it b naught, it will be 0. But we also have to define what will be my next state. So if bi, let's go back here. In this, if bi is equal to 0, I will stay in the same state. Yeah, let's put it if bi is equal to 1, then next state will be the state b. Else you will stay in the same state. Else next state is the same as the current state. And if then the second value of the identifier when b, again output will be 0. Again I will have to check on bi. So if bi is equivalent to 0, then only next state will be c. Else I'll continue to stay in the same state. Else next state will be the same state, as you can see here. Fine. Again I will end this if. Similarly, I will have the third value for the identifier when c. Again, when I am in the state c, b naught will be 0. And then again, I will check for the condition if bi, now see, if bi is equal to 1, then I will move to state d. Fine. So if bi is equal to 1, then in that case, my next state will be the state d. Else, if it is not the case, then I will move to the initial state. Else, my next state will be the state A, and if then the final value of the identifier when D. So in that case, now B out will be 1 because the sequence has been detected in state D. Not only that, the current sequence has been completely detected and the first bit of the next sequence has also been detected. Fine. So from here on, I can either go to the state C or I can go to the state B. So B naught is equal to 1. Then again, I'll put a condition that if Bi is equal to 0, then next state will be the state C, as you can see here. And else next state will be the state B. I will end if, I will end the case, I will end this current process, and then I will end the architecture, whatever the name is. Fine. This will code this design based on the Moore machine. Right? Now, suppose we have to design the same thing using the Mealy machine, where the outputs are conditional; they're not defined for a particular state. Right? Let's draw the Mealy machine for this thing. So again, let's say I have a state A. This is my initial state as specified by this small arrow. Fine. Now I can't be explicit about the output. I don't know what the output is in this state because it is conditional. It will depend upon the nature of the input. But what I know is that I am looking for the first bit of the sequence, which should be 1. So if I don't receive 1, I have a 0. I will continue to stay in the same state and my output will be 0. And if I receive 1, I will move to the next state. Let's call that state B, but my output will still be 0 because the sequence is not complete. Fine. Now in this state B, I can move to the third state if I receive 0. And if I don't receive 0, I receive a 1, I will continue to stay in the same state. Because this state means only the first bit has been detected. So if I have the input equivalent to 1, I will continue to stay in the same state, output will be 0. But if I have B input equivalent to 0, then I will move to the third state, state C. Fine. Now in the state C, again, I can have two conditions. Fine. And the first condition will be, just a second. So if I'm looking for the sequence 101. So I have detected 1, then I have detected 0. Fine. So from the C state, the next one I'm looking for is 1, because if I get a 1, then only my 3 bits of the current sequence have been detected. And if I, as like I said, that this one, the third bit of your current sequence is actually the first detected bit of the next sequence. So if I receive 1, I will move to state B and my output will be 1. Fine. And if I don't receive 1, if I receive 0, I'll have to start from the scratch. So something like this. Fine. So this will be the melee behavior. And as you can see, I have reduced one state. Fine. And if you actually trace the path in the state machine, which is the desired path for the sequence to be detected, it will be something like this. We start from A. Should use a different one here. Then B. In B, my first bit has been detected. Then in C, second bit has been detected. And from C, if I go back to B, then only my sequence has been detected. Fine. So this is the melee behavior. And the coding strategy will be the same. You'll start with, as usual, library declaration, then you will define your ports in the entirety. In the architecture, you will first define a user-defined data types by the name, whatever you want to like. Typically, we use state. And that state will have only 3 values, A, B, and C. Moore machine, we had 4, A, B, C, and D. Then you will initiate a process for the implied clock. And you will initiate second process wherein you will use the case statement. And within a particular case, you will have 2 if statements. Fine, because this is a Moore machine. And in a particular state, the output is not implied. You have to be very explicit. You have to mention the condition. Okay, what will be the output. So that will depend upon for example, take this as an assignment, but I would like to show that the first case, the first value of the case will be case previous state is So when A, then again it will depend upon the value of Bi. So if Bi is equivalent to 0, then output will be 0. Fine. And next state will, you'll stay in the same state. So next state will be A. Else, although in this case, whether it is 0 or 1, output will be 0. So else I can say B naught is still equivalent to 0, but the next state will be state B. Something like this. So give it a shot. Try to code this using the Mealy machine. And then synthesize it, write a test bench, and just see whether it behaves in the desired way or not. Fine. So this is yet another important circuit that we often use in at the, I mean, in the encryption, in the error detection or an encryption decryption. These sequences, they play an important part. Now, typically we don't use 3-bit sequences in the practical scenario. You will have to detect a large 8-bit sequence, 16-bit sequence, the current standard, whatever the standard is. But this is the way we do it. Fine. Is maybe we use the finite state machine approach. So state machines are very, I mean, very much everywhere. In fact, your protocols for your network, TCP/IP, those protocols are also designed using the state machine approaches, either the Moore machine or the Mealy machine. So this is the sequence detector. Try it out in the lab. I will also give you another assignment based on this sequential circuit design that I will pass in the group. And there will be some examples based on these sequence detectors, based on the counters that you can using the same method. So this is basically a kind of a, like I said, the kind of a framework or a kind of a template for designing the sequential circuit. There are multiple templates, but personally, I feel this template wherein we define a previous state and next state using a user-defined data type, then initiate a first process that defines your implied clock, then initiate a second process that defines the output in each state and the condition from which we can move the current state to the next state. I think this is a very trivial and a very straightforward template. And if you have the correct description of your circuit in terms of a finite state machine, can actually design any sequential circuit. Right? So I'll be passing on the assignment and you try to design those circuits using VHDL. Thanks.